let us finish our discussion of section 1.2, first order linear differential equations. Last time we started with the following definition. The general first order linear differential equation is this. Now, we discussed so-called homogeneous first order linear differential equations. Homogeneous means the right-hand side is equal to 0. Here is the general solution of such an equation. Today, we will discuss the general case. What if the right-hand side is not equal to 0? We call such equations non-homogeneous. So, there are two ways to find the general solution. Way number one is to use this formula where mu of t is equal to this. However, this formula is harder to remember than the previous one. Therefore, I would rather suggest a step-by-step process. So, what you really need to remember is this formula for mu. By the way, note that this formula is very similar to the formula for the general solution of homogeneous. Let us actually compare. Please take a look at this. So, over here, we have the general solution of a homogeneous first order linear differential equation. There are two differences. There is no c here and there is no minus here. But please don't be surprised. The nature of these two formulas is very different. This formula gives us, as I said, the general solution of a homogeneous first order linear differential equation. This formula has nothing to do with the general solution. This is just a term in this formula. So it should not be a surprise that these two formulas are different. The nature of mu of t and y of t is different. Now you may ask me a question, why there are similarities? The reason is the following. If you click on explanations, mu of t is a solution of this homogeneous first order differential equation where in front of a of t we have minus. This is the reason why over here there is minus, but over here there is no minus. Lastly, mu of t is a particular solution of this homogeneous first order linear differential equation. Therefore, we skip c in front of e. Now, why do we need mu? Mu is part of this bigger formula. Therefore, as I said, in order to find the general solution of this, either you use this formula in combination with this, or we apply this formula first and then use a step-by-step process that we are about to discuss. So, please take a look at this equation. Obviously, this equation is not homogeneous because the right-hand side is not equal to 0. So, step 1, find mu. Mu of t is equal to e to this power. In order to apply this formula, first we have to identify a of t. In our case, a of t is negative 2t. Common mistake. Sometimes students forget to put minus sign. So a of t is not 2t because we have minus in front of the whole thing. So a of t is negative 2t. Antiderivative of negative 2t is negative t squared. Therefore, mu of t is e to negative t squared. After that, either we plug in this mu into this formula and find this integral, or we apply the following step-by-step process. So, step 1, multiply both sides of this equation by mu that we just found. Done. One can check that the left-hand side of this equation is equal to derivative of mu times y. Well, let us check it. Click on y. Note that if we expand parentheses over here, we get exactly what is written here. On the other hand, if we apply the product rule in order to find the derivative of this, we'll get the following. Derivative of this expression is equal to y prime times e plus y times e prime. In order to find the derivative of e to negative t squared, we use the chain rule. If we think about negative t squared as about u, e to u prime is e to u times u prime. And negative t squared prime is negative 2t. Note that what is written here is exactly what is written here. Conclusion, indeed, the left-hand side of this is equal to derivative of mu times y. Now, this is not a coincidence. Theory says that if we multiply the left-hand side of our first order a linear differential equation by mu that we find using this formula, the whole left-hand side becomes derivative of mu times y. Here's what we do next. We integrate both sides. Done. And then click on work. Antiderivative kills derivative. So the left-hand side becomes mu times y. On the right-hand side, in order to find this integral, we use u substitution. Let us denote negative t squared by u. We put d from the left, d from the right. Derivative of negative t squared is negative 2t. Now, here there is no negative 2. Therefore, next step, divide both sides by negative 2. After that, we replace t dt by negative 1/2 du. Done. We replace negative t squared by u. Done. Antiderivative of e to u is e to u. Back substitution, the result falls. So here is the general solution of our equation written implicitly. Now, in order to come up with an explicit formula, just move this term to the right. Here is work. In order to move this term to the right, one way to do it. We multiply both sides of this equation by e to positive t squared. Next step, we expand this parenthesis. Done. Then observe that e to t squared times e to negative t squared is equal to e to t squared minus t squared. Similarly here, this is equal to e to negative t squared plus t squared. Obviously, this is equal to 0. This is equal to 0. E to 0 in both cases is 1, and the result false. Any questions?
So would mu basically be our integrating factor?
Yes, mu is our integrating factor. The goal of mu is the following. As I said, theory says that if we multiply the left-hand side by mu, this expression can be rewritten as derivative of mu times y. In general, we explain why this happens in explanations. But in our particular case, work is here. It is easy to check that indeed derivative of this, which is over here, is equal to this, which is over here.
Thank you. Yeah, I was confused there as well, but that explains it.
Can you repeat the last part where you multiplied e to the t squared with e to the negative t squared?
Yes, so see, sometimes students get lost when they see something like this. So question is how to move this to the right correctly. One way to do it is the following. Let us multiply both sides of this, which is over here, by e to positive t squared. So on the left, e to positive t squared, on the right, e to positive t squared. And then observe that what is written here is e to 0 power, which is y. So on the left-hand side, we have y. On the right-hand side, after all simplifications, we get this. Do you want me to go over?
No, that's good. Thank you.
Any other questions?
Yes, sir. I have a question for you.
Yes.
So you said that this works for first order non-homogeneous differential equations. But for example, if we have something like a y squared, so if it's a of t times y squared, can we can still use the mu of t to help us differentiate, right?
No, this theory can be used only for linear first order differential equations. So if instead of y here we have y squared, this theory cannot be applied.
Okay, so then the only way we'll be able to solve it is if it's a separable equation.
Well, yes, we will discuss it later today. We'll discuss separable. So if our equation cannot be written as first order a linear differential equation, we try to apply other methods. For example, the method of separation of variables.
Okay. Thank you, sir. Thank you.
Sure. Other questions?
Can we go over one more time the use substitution that we did?
Yes. So here is what we do. Step 1, let us denote negative t squared by u. Next step, we put d from the left, d from the right. After that, we take the derivative of negative t squared, which is negative 2t. And then, since there is no negative 2 here, we divide both sides by negative 2. Here is the result. Next step. By the way, big picture is the goal is to get rid of t terms and obtain only u terms on the right. T is not allowed here. Should be only u terms. Number 2, this integral should be from the list of standard integrals from calculus 1. And by the way, here is the list. We go back to my calculus website over here, click on substitution rule, and here is the table. Well, obviously, This integral is not in the table. However, this integral of e to u du, is over here. It's e to u plus c. This is how we jump from here to here. And then back substitution, u, according to what is written here, is negative t squared. This is how we come up with this answer. Did I answer your question?
Yes, thank you.
Any other questions?
For step 3, underneath the u substitution, what if you divided by e to the negative 2 squared on both sides?
Very good point. So there are two ways to jump from here to here. Either we multiply both sides by e to t squared, or, which is fundamentally same, we divide both sides by e to negative t squared. Absolutely.
Okay, thank you.
All right, next example. Over here, we have the initial value problem. How do we solve it? So, as before, step 1, find mu. Here is the formula. We replace a of t by 2t. Indeed, looking at this equation, a of t is positive 2t. Antiderivative of 2t is t squared, so the integrating factor is e to t squared. After that, as before, we multiply both sides by mu, and again, one can check that the left-hand side is equal to derivative of mu times y. Now we can proceed in two ways. Way number 1, integrate both sides. Antiderivative kills derivative. So the left-hand side becomes mu times y. The right-hand side, by u substitution, is 1/2 e to t squared. So guys, since this integral is very similar to the previous one, I don't go over steps. Basically, the only difference, instead of negative t squared, we have t squared here. Here's what we do next. In order to find c, we use the initial condition y of 1 is equal to 2. How do we do that? So we replace t in both cases by 1, because here we have 1. We obtain this, and of course y becomes y of 1. Next, e to first power is e. E to first power is e. According to what is written over here, y of 1 is equal to 2. We move 1/2 e to the left, done, and 2e minus 1/2 e is equal to 3/2 e. So c is equal to 3/2 e. We replace this c by 3/2 e, done, and then we simplify a little bit. We multiply both sides by e to negative t squared. This disappears because it's 1. On the right hand side, if we expand parentheses and simplify a little bit, we get this. So the result follows: y of t is equal to 1/2 plus 3/2 e to 1 minus t squared. Folks, any questions here?
Can you go over the last part again?
Yes. So over here we have the general solution of this equation alone. But now, in order to find this c, we use the initial condition. How do we use it? Step 1, replace t here and t here by 1. Done. Then replace y of 1 by 2. Done. Simplify a little bit. C is equal to 3/2 e. So we replace c here by this expression. Done. After that, move e to t squared to the right. Work is here written. And simplify a little bit. Do you want me to go over these steps?
Yes, yes. This is the part where I needed like more clarification.
All right. So here's what we do. So first of all, if we multiply both sides of this by e to negative t squared, we obtain this expression. Do you understand this?
Yes, yes.
Next, we expand parentheses, we distribute. We multiply this by this, done, and this by this, done. Also observe that e is equal to e to first power. After that, put together exponents. Negative t squared plus t squared, done. T squared plus negative t squared, done. 1 plus negative t squared, done. Note that this and this is 0. We put 0 here, 0 here. E to 0 is 1. E to 0 is 1. The result follows. Did I answer your question?
Yes, yes. Thank you. That helped a lot.
Any other questions, guys?
Can you go back to where you solved for C really quick?
For C, yes, absolutely. Are you talking about this?
Yes.
So here's what we do. We start with this formula. In this formula, we replace t by 1. For example, if here 7, we replace t here and here by 7. But here we have 1. So we put 1 here, 1 here. Done. And we replace y by y of 1. Done. Do you understand this step?
Yes.
Then, according to what is written here, y of 1 is equal to 2. So we replace y of 1 by 2. 1 squared is 1, and e to first power is e. Again, e to first power is e. Then move this to the left. Done. And 2e minus 1/2 e is 3/2 e. Did I answer your question?
Yes, thank you.
Any other questions?
Will there ever be a case where there are bounds to the integral?
Yes. Excellent question. Now let us click on way 2. Over here. So please compare. In way 1, we use indefinite integral. However, way number 2, we integrate both sides from 1 to t. Here we put 1 because the initial condition is y of 1. For example, if instead of 1 we have, say, 5, we put here 5 and here 5. Here's what we do next. Antiderivative kills derivative. Done. But since we have integral from 1 to t, we put vertical line from 1 to t. Same as here, as we discussed, antiderivative of this is 1/2 e to s squared, then vertical line from 1 to t. After that, vertical line means this at t, which is over here, minus this at 1, which is over here. Similarly here. Lastly, y of 1 is equal to 2. And after all simplifications, we get this result. And if we move e to t squared to the right, this. Was that your question?
Yes, yes. Yeah, that. I was just wondering, like, if that to some extent, I feel like this one's kind of simpler.
Well, again, this is the reason I provide 2 different approaches. So if you prefer way number 1, this is your choice. Some people like way number 2 better. Folks, any other questions?
So, sir, basically for the second way, what we're doing is we say that s is our function, and then t equals 1 and S equals 1 and S equals t are the two bounds that we're looking at.
Yes, absolutely. It's exactly what we do. So we replace here S by t, done, and S by 1, done.
Okay, thank you.
Any other questions?
Sometimes like solution 1 and solution 2 have different answers. Like if you plug in a variable for like a constant in C, on the exam, like would you care which one we used? Or like since it's multiple choice, would you have answers that reflect both of the ways of solving or only one?
Excellent question. Indeed, sometimes we apply different methods and we get a little bit different solutions. But one answer can be rewritten as the other answer if you apply methods correctly. So if your answer is different from any answer from the multiple choice, then either the answer is none of the above, or try to find either a mistake in your solution or try to rewrite your answer as one of the listed answers. Was that your question?
Yes, thank you.
Next. Here's another example. Let us take a look. Step 1, we find mu. Mu is equal to e to integral of x dx, yx, because we have x in front of y. Antiderivative of x is x squared over 2. Then we multiply both sides by mu. Done. And again, one can check that the left-hand side is the derivative of mu times y. The right-hand side is the following. E to x squared over 2 times e to x squared over 2 is equal to e to x squared over 2 plus x squared over 2. But x squared over 2 plus itself is x squared. It's exactly what is written here. Another way to think about it is the following. What is written here is simply e to x squared over 2 squared, which is e to x squared. So we jump from here to here, and then we integrate both sides. Antiderivative kills derivative. Done. As we discussed, by u substitution, antiderivative of x e to x squared is 1/2 e to x squared. And of course, we put plus c here. Then we move this term to the right. Again, work is written over here. And now it's time to find c. So we use the given initial condition. We replace x in all three cases by 0. Y of 0 is equal to 1. We replace y of 0 by 1. E to 0 is 1. E to 0 is 1. And after simplifications, we get exactly what is written here. Move 1/2 to the left. 1 minus 1/2 is 1/2. So c is equal to 1/2. Lastly, we replace c here by 1/2 and factor out 1/2. We get this, which can be rewritten as this expression. Work is here. Folks, think about questions.
Can you go over the last part where the e to the x squared over 2 that is next to the y, like?
So your question is how we jump from here to here?
Yes.
So here's how we do it. We copy this expression. It's over here. Next step, we expand parentheses. This times this, which is over here, plus 1 times this. Done. Then we put together exponents. Here times, therefore here plus x squared plus negative x squared over 2 is x squared minus x squared over 2. And now x squared minus x squared over 2 is x squared over 2. The result follows. Did I answer the question?
Yes. Thank you.
Folks, any other questions?
So what did C end up being equal to?
In our case, c is equal to 1/2. If you replace c by 1/2 here and factor out the common term 1/2, you will get this.
Can you go up a little?
Yes?
Yes, thank you. On the integral on the left side of, yeah, you use what's it called? Integration by parts, right?
No. Antiderivative kills
No.
derivative.
On the one on the right?
Or on the right, no, it's u substitution. We denote x squared by u, d from the left, d from the right. Derivative of x squared is 2x. And since there is no 2 here, we divide both sides by 2.
Oh, yeah,
Now,
I didn't see it before, sorry.
Yeah.
Go ahead.
And then the result follows.
All right, thank you.
Any other questions?
Can we use the same second method of applying bounds to solve this?
Yes, absolutely. If you use way number 2, you integrate from 0 to x. Here integral from 0 to x, here integral from 0 to x, and instead of x, you use some different letter, for example, s.
Okay, thank you.
Last problem. Note that this equation is not written in the standard form. Here is what I mean by the standard form. Please take a look at this. We start with just y prime. There is nothing else on the front. Here, in front of y prime, we have x. So folks, common mistake. Sometimes students looking at this say that a of x is equal to 2. No, the answer is no. In order to identify a of x, first we have to rewrite this in the standard form. We divide both sides by x. Done. And now a of x is equal to 2 times x to negative 1. Next step, find mu of x. And now, please be careful. So, mu of x is e2 integral of a of x dx. A of x is 2x to negative 1. We factor out 2. Antiderivative of x to negative 1 is ln of absolute value of x plus c. But remember, on this step, we do not put plus c because we care about only a particular antiderivative. So there is no plus c here, and also there is no absolute value because it's written x is greater than 0. So here's our mu, e to 2 times ln of x. But now, for the first time, we simplify our mu. Here's why. Remember, next step is to multiply both sides by mu and then integrate the right-hand side. Integration is a pretty complicated process. Therefore, we have to write mu in the simplest possible way. So how do we simplify this? Well, first, for convenience, let me switch positions of 2 and ln. 2 times ln is equal to ln times 2. After that, let us put parentheses around the whole thing here. So e to ln of x times 2 is equal to e to ln of x, the whole thing squared. And it is known that ln kills e. E to ln of x is equal to x. So mu of x is equal to simply x squared. After that, as before, we multiply both sides by x squared. x squared times x to negative first power is x, one can check that the left-hand side can be rewritten as derivative of mu times y, and then we integrate both sides. Antiderivative kills derivative. Done. Integral of x cosine of x dx is equal to this. Folks, who can tell me how we jump from here to here? Which method do we use?
By parts.
Integration by parts. Let us look at work. So, we have to use the integration by parts formula. Folks, very often I call the integration by parts method UDV substitution, because in order to apply this formula, first we have to decide what is U, what is dV. But for U, we have a bunch of possibilities. Is it x? Is it cosine? Is it x times cosine? What do we do? Well, guys, let us go back to my calculus website. Here are three cases. Case A. If the expression inside of integral is of the form x times e, or x times sine, or x times cosine, we denote by u this. In our case, we have x to first power, u is x. The rest, which is cosine x dx, is dv. Two other cases, if we have ln or inverse trig functions, we denote by u either ln or trig function. The rest, which is x to a dx, is dv. Last case, if we have combination of e with either sine or cosine, basically it does not matter. We can denote by u either this or sine or cosine. Anyways, in our case, x is u, cosine x dx is dv. But what do we do next? Well, know that here we have two parts. In this part, we put d from the left, d from the right. Over here, in order to find v, we find an antiderivative of cosine, which is sine. Now we can apply the formula. U, which is over here, is equal to x. We put x. V, which is over here, is sine of x. We put sine of x. We copy minus, we copy integral. V is equal to sine, we put sine. Du, which is over here, is dx. We put dx. Lastly, antiderivative of sine is negative cosine, and minus times minus is plus. The result follows. Very last step, if we move x squared to the right, we get exactly what is written here. Folks, any questions?
If an equation isn't in standard form, will our first step always be to rewrite it so that it is?
Yes, absolutely. Step one, rewrite your equation in the standard form. And by standard form, I mean this.
Okay, thank you.
Any other questions?
Could you go over the derivative, like the e, or the derivative of the 2x minus 1?
Derivative of 2x.
I mean, the integral of 2x minus 1. Oh, it was like at the...
here,
yeah.
yes. So, question is how we jump from here to here?
Yes, I mean, I'm assuming like you can factor out the 2.
Yes. First we factor out 2, and then inside integral we have x to negative first power. And if we go back to this table, integral of 1 over u du is ln of absolute value of u plus c. In our case, Instead of u, we have x, because 1 over x is x to negative first power. And then we do not put plus c, because here we care about only a particular derivative, and we do not put absolute value because x is greater than 0. Was that your question?
Yes, thank you.